we're going to have a look at solving periodic functions in this little video. We're not going to look at anything massively complex. We're only going to be dealing with values that we can solve using the unit circle. I'll do another video when we're solving functions, values of functions where the angle might not come out perfectly and we'd have to use our calculator to figure out the angle or the radian measure in order to solve it. But for these two examples, we're going to be solving it both algebraically and graphically using our unit circle values. So, as a first example, let's have a look at y equals 4 sine x plus 1 over a domain from 0 to 2 pi. And let's solve it for when y is equal to 3. Okay, whenever we're solving it whenever we're solving a function graphically, we need to do a quick sketch. So let's do a quick sketch. To remember to sketch, we write down A, that's the amplitude. We write down B, which is the horizontal dilation factor. And that means, because our B value here is 1, that means our period is really easy to figure out, because remember that period is equal to 2 pi over B. Now notice that matches up really nicely with my domain, because my domain is from 0 to 2 pi. My period is 2 pi, so that means we only have to draw one wave. That's nice, nothing tricky going on there. And then we have D. D is equal to 1, so that's my vertical translation factor. The whole function is going to be moved up 1. Okay. So, draw the axes, mark in some of the scale. Okay, we're going up 1. That's going to be my midline. So draw my midline in there. The maximum is going to be, we have an amplitude of 4 on this wave, so the maximum is going to be at 5. And we have a minimum of -3. Same deal, 4 up, 4 down. Okay, I'm going to draw out some little lines in just to give me a guide to draw to. That's going to help me when I'm sketching it. And my period is 2 pi. So I just need to split that up into quarters. Okay, it's a sine wave. So remember, with sine waves, we start in the middle, we go to the max, we come back to the middle, we go to the min, come back to the middle. So, middle, max, middle, min, middle, and join those points up. Now remember, when we're trying to solve graphically, we need to do the best sketch that we can so that we can get a good approximation. I'm now going to draw the line in y equals 3. Draw the line in there. That's the line y equals 3. And to solve, we're trying to find the point where those two lines cross over. Those two functions cross over. Oh, I've just lost my y equals 3 line. There we are. Okay, so let's approximate it. Here are our two solutions graphically. Now, because our domain, our period is 2 pi, that means half of the wave is pi, so this is pi on 2. I know that I have one solution that's between 0 and pi on 2, and another solution that's between pi on 2 and pi. Now, because we're working in radians, it can be really hard to approximate exactly what we've got, but by having this little sketch, I'm going to be able to check really well the validity and the reasonableness of my algebraic solution. So if my algebraic solution doesn't match up with what I've got graphically, I know that I've made an error. So algebraically, to solve this, we let the y equals 4 sine x plus 1, we let that equal 3. So we're going to have 3, 4 sine x plus 1. And we've got our domain from 0 to 2 pi. Okay, rearrange, so we're going to have to subtract the 1, so we get 2 equals 4 sine x, divide by 4, so we get a half equals sine x, and then we solve. So we know that in the first quadrant, the angle or radian measure that is sine of that angle equals a half, we know that's pi on 6. So that gives us our basic angle. Pi on 6 occurs 4 times around the unit circle, and if we have positive a half, that means we're in quadrant number 1 or quadrant number 2. So therefore in this case x is equal to pi on 6 or 5 pi on 6. Two of our nice values from the unit circle. Now let's have a look. We've got one value that's between 0 and pi on 2, and then we have another value here that's between pi on 2 and pi. So when I have a look at my algebraic solutions compared to my graphical solutions, I'm like, yes, they match up. That makes sense. My algebraic solution is therefore reasonable. It's a really good way of checking your solution. Or if you're running out of time, drawing the graph is a really good way of coming up with an approximate solution if you don't have time to solve anything algebraically. So let's have a look at another example. This is going to be an example where my domain is not going to be in radians. So it might even be a little bit easier to approximate a solution. So we're going to have a look at the function y equals 2 cos pi on 4x plus 4, and we're going to try and solve it from y equals 3. Okay, once again let's sketch. A equals 2, b equals pi on 4. Therefore the period equals 2 pi divided by pi on 4. Remember, when we divide by fractions we multiply and flip, so the period is equal to 8. Now let's see what happens with our domain. My domain is from 0 to 8. My period is 8. That means we have to draw one wave. That makes it nice and easy for us. The d value, our vertical translation factor, is 4. So let's do a quick sketch. Bit of a scale on my y-axis. Okay, my d is 4, so I put the midline in at 4. My amplitude is 2, so my max is 6 and my min is 2. Guidelines in for each of those. Period is 8, mark that in. Mark in the quarters. Mark in the quarters, there we go. Okay, we're now ready to sketch. Remember, cos functions goes max, middle, min, middle, max. And we're going to, as best we can, draw a nice, neat cos function. There we go. Now we're solving this for y equals 3. So let's draw in the line y equals 3. Here's 3, y equals 3 cuts across here. And we can see that there are two solutions. We have two solutions, one here and another here. If we come down to the axes, we can come up with a bit of approximation as to what they would be. We can look at our axis that the period was 8, so that means halfway is 4, half of that is 2, and then 6. Let's have a bit of a guess at what this might be. I know I'm having a look at my graph. That's 3 there. So I think this value here is 2 and a bit. I'm going to guess that it's going to be 2.7. Now this one here, I know that that is 5 there. So it's somewhere between 5 and 6. I'm going to have a guess that this is approximately 5.6. So let's test our solution, our graphical solutions, our graphical approximations with the algebraic solution. Remember, the graphical solutions are something that can give us a good idea of what's going on. So algebraically, I'm going to let the function equal 3. So I've got 3 equals 2 cos pi on 4x plus 4 over the domain from 0 to 8. And then I have to rearrange. Minus the 4, minus 1 equals 2 cos pi on 4x, divide by 2, negative a half equals cos pi on 4x. Now this is one of those functions where we can't solve this in this form. We're going to have to do something a little bit cheeky. I'm going to let a equal that nasty angle. That angle there's a little bit messy for me. So I'm going to rewrite it as -1/2 equals cos A. That's something I can solve. That's really nice and straightforward. But in order for us to do this now, I need to change the domain. My last domain was in X. I now need to have a domain that's in A. Now A is equal to 4 pi, pi on 4x. So and my domain was X, so I have to multiply this domain by pi on 4. So that's going to be 2 pi. Now I'm ready to solve. The basic angle, the angle or the radian measure that makes cos equal 1/2 is pi on 3. So that's my basic angle. Pi on 3 occurs 4 times around the unit circle, and we're looking for the -1/2, the negative value, and that occurs in quadrant number 2 and quadrant number 3. So therefore, I know that my angle in this case is 2 pi on 3 and 4 pi on 3. Now they're two wonderful answers. They're really fantastic. Nothing wrong with that. However, we weren't looking for A, we were looking for X. So we now need to turn it into X. Now I know that A was equal to 4 pi on 4x. So therefore, if we rearrange that, X is equal to 4 on pi times by A. So if we write out X here, we need to take all of the A values and multiply them by pi on 4. 4 on pi, I'm getting them all mixed up. 4 pi on 3 times by 4 on pi. Okay, so therefore we get X is equal to 8 on 3 and X is equal to 16 on 3. Now if I write them out as their decimal approximations, we'll be able to check whether or not they match up closely or not so closely with our graphical solutions. So 8 on 3 is 2.6 recurring. 16 on 3 is 5.3 recurring. Okay, let's have a look. Oh, look at that. That's a fantastic guess that we did for our first one. So my graphical solution and my algebraic solution for the first value match up really well. That's a really good approximation that we made there. And my second one, 5.3 recurring and 5.6, they're not as close, but they're in the right space. So my graphical solution does agree with what I found algebraically. So I would assume if I was writing this out quickly in a test and I wasn't able to check my answer with anyone else, I'd be like, yes, I have made a good algebraic solution there. It matches my graphical estimate really, really well. Okay, guys, I'm going to do one more example of solving periodic functions where the function isn't going to come out nicely. The solution is not going to come out as a perfect value. But for this is the example of how you would do it if we're going to use nice values straight from the unit circle. So I hope that worked. I hope that helped. Please let me know if you need anything else. Talk to you soon.